In this video, we're going to talk about the exponential decay of the intensity of the radioactive beam. First of all, we're going to talk about what the intensity of the radioactive beam and what does it mean, the exponential decay, first of all. So the intensity of the beam can be considered as a number of the photons per unit of area, for example, per 1 square centimeter squares. For example, it's possible that I've got a beam which has 15 photons per 1 centimeter square, and another beam, the blue one, which has 10 photons per 1 centimeter square. So in this case, I say that this beam is more intense than this one, even though the energy which is associated with the red beam is going to be lower than the energy associated with the blue one. And what does it mean, the exponential decay? So let's assume that you've gotten 64 apples, and what you need to do is you need to distribute half of the amount of this apple every hour. So let's say in the beginning, at the initial time, t is equal to 0, you've got 64. After 1 hour, you have to distribute 32 of them, and you're going to have 32 apples. After 2 hours, you have to distribute half of the 32, which is going to be 16. So you will have 16 apples. After 3 hours, you have to distribute half of the 16, which is going to be 8, and so on. So what I would like to do is I would like to just write down this table as a mathematical formula, which is going to allow me to find the amount of the apples which I have at any arbitrary time, so that after any number of hours. So let me write it. So initially I used to have 64 apples, right? So after 1 hour, I have to have like half of this, or 32. In order to do this, I have to just multiply the 64 to the 1 over 2. So I'm going to have 32, right? So if I would like to know how many apples I'm going to have after 2 hours, I have to multiply 32 to the 1 over 2, or 1 over 2 is going to be multiplied to here, and I'm going to have 16 apples. And after 1 hour more, I have to multiply this to the 1 over 2 in order to have 8 apples. So do you see? So the number of the apples are decreasing twice at every hour, and we call this decrease as exponential decrease. So I would like to write down this as a formula. So please note that you can write down the 1 over 2 as a 2 in the power of minus 1. So this is going to be 2 in the power of minus 1. This is going to be 2 in the power of minus 1. So the multiplication of the 2 in the power of minus 1 3 times, it's going to be 64 multiplied as a 2 in the power of minus 3. So this is the amount of the apples which I'm going to have after 3 hours. So the amount of the apples which I'm going to have after 1 hour is going to be 64 multiplied as a 2 in the power of minus 1, right? Only this part. The amount of the apples which I'm going to have after 2 hours is going to be 64 multiplied as a 2 in the power of minus 2. After 3 hours, it's going to be 64 multiplied as a 2 in the power of minus 3. And so on. So can you guess what's going to be the number of the apples which I'm going to have after 4 hours? It's going to be 64, 2 in the power of minus 4, right? And so on. So in general, we can write down the number of the apples which we are going to have after 2 hours. It's going to be 64. So the initial number of the apples which we have multiplied is a 2 in the power of minus t. Right? So if you just substitute the 0, you will get 64. If you substitute the 1, it's going to be 32. If you substitute the 2 to here, it's going to be 16, and so on. So this is just a formula of the exponential decay. So in general, we say that whenever the X-ray beam or the gamma ray beam hits within a material, it's going to lose the intensity exponentially. So in the power of some constant, in the power of minus t time or distance, and so on. So let's assume that I've gotten beam with initial intensity I0, and as it passes through the material, it's going to lose its intensity. What I would like to do is I would like to know at some point x, so at the distance from the beginning until here, let's say, it's going to be x centimeters. Okay, so this is so if this would be 0, then this point would be x. Then the distance is going to be x centimeters. I would like to know what's going to be the intensity. here. So it appears the intensity formula is going to be constructed very similar way in this one. It's going to be the initial intensity multiplied to the e in the power of minus x, more or less like this. Okay, so the only problem here is, so this formula just takes into the consideration just the distance, how far I'm away in this material. So basically it tells me that as far away I'm going to go through this material, I'm going to lose my intensity, right? So this formula doesn't basically take into account that so the different materials might have different absorption. So let's assume, what does it mean? So let's assume that I'm going to send like a 50 gamma ray photons to one material, and after 2 centimeters the number of the gamma ray photons which I'm going to have is going to be 25, let's say. So this is going to be I, this is I0. Okay, if I send the same gamma ray photons like I0, which is equal to the 50, to another material, so let's assume that after 4 centimeters the number of the gamma ray photons is going to be 25 units. Okay, so you see, so this material absorbs the gamma ray photons better than this one, right? So let's assume that mu1 is going to be some material parameter for the first material, and mu2 is going to be some material parameter for the second one. Okay, so depending on the material, the absorption might be faster or slower. So basically, I would say that mu1 is bigger than mu2 because the first material absorbs the beam better than the second one. So in order to fulfill this formula, this one, I just need to put here the mu it appears. So now this formula is complete. So it's going to tell us what is the intensity of a beam, of the X-ray beam or the gamma ray beam, which is passing through the material at the thickness level X with the material parameter mu. So this material absorption parameter mu is also called as an attenuation coefficient. So well, it appears if I draw this formula, I'm going to have roughly this kind of graph. So this is the graph when I is equal to the I0 e in the power of minus mu x. So let's assume that I've gotten beam with incident intensity level I0. So as it passes through the material, for example, at the level x centimeters, I measure its intensity. I would like to know, okay, so if I have this intensity here after x centimeters, what is actually this mu, the attenuation coefficient? Right? So if I know everything here in this formula except this mu, is it possible to find this mu? So well, it appears yes, we can find this. In order to do this, we just need to do a couple of simple mathematical operations. So what I have to do is I'm going to divide both of the sides of this equation to I0, so that I'm going to have I0 here. I over I0 is equal to the e in the power of minus mu x. So you see, so this mu is in the power of the exponential number, so I just need to get rid of this e. So in order to do this, I'm going to take the ln from this part and ln of this part. So we know that ln of something in the power of this number, so this can go down. Then I can write this down in the form of ln of I over I0 is equal to the minus mu x multiplied to the ln of e. So which is simply is equal to the 1, right? Because ln is the logarithm with the base e. So what I have here is mu x is equal to the minus ln of I over I0. And if I would like to find the mu, the attenuation coefficient, I just need to use the formula. So minus ln of I over I0 multiplied to the 1 over x. So basically from this equation, I'm just dividing both of the parts to say x, and I'm finding this formula for the mu. Good. So this is the general formula to finding the mu. The only thing is, my first observation is that I don't actually need to know the I0 and I, both of them. So I just need to know their ratios. What does it mean? It means that if I know that after x centimeters, after, for example, 2 centimeters, I've lost 50% of the intensity, I can find the attenuation coefficient. For example, if the I is equal to 500, if this is the 250, this is going to be loss of the intensity by 50%. Okay, so we don't need to actually know I and I0, both of them. We just need to know the ratio. So that is why most of the time we can see the graph for the attenuation coefficient or the intensity in this form, where here it's going to be not simply I, the intensity, over the thickness, but I over I0. So how much intensity still we have, right? So it's going to be I over I0 is equal to the e in the power of minus mu x. So we are going to find this mu in the two different ways. The first way is, so do you see, so if I have this formula, I over I0, right? So at maximum, it might be equal to the 1 when I is equal to I0, right? When it is equal to the I0, when x is equal to the 0. So before we enter the material, the intensity here at the x is equal to the 0 is equal to the I0, right? So that is why I over I0 is equal to the 1 here, right? When x is equal to the 0. As we go through the material, the intensity is going to be changed. For example, I over I0 is equal to the 0.5. It means that we've lost 50% of the intensity, and we actually have, so the current intensity is the 50% of the initial one. So let's assume that I know that at some point x, the I over I0 is equal to the 0.5. So how to find this? So basically, I over I0 is equal to the 0.5. Here, I need to find this point. Okay, then I need to go to the x line here, and I need to find the x. So let's assume that this x is equal to the 1.25 or something this, right? So at x is equal to the 1.25, the intensity, the current intensity is the 50% of the initial one, okay? It's equal to the 1.25. So what's the attenuation coefficient? So if I would like to find this, I'm just going to use this formula, right? So it's going to be ln of I over I0 is equal to minus mu x. From here we can find it. Mu is equal to the minus ln of, so I over I0 is 0.5 divided to the 1.25. So I'm going to use the calculator in order to calculate this. It's going to be ln of 0.5 over 1.25 and multiply this as a minus. It's going to be 0.5545 roughly, right? So this is the one way how to find this. So this called as the half thickness value intensity. So half layer value. Okay, so it's basically if I know at which point x I've lost 50% of the intensity, then I can just use this formula, so which can be rewritten. So if I over I0 is equal to the 0.5 at some point x, then the mu can be found as the minus ln of 0.5 over the x. Or we can write down this 0.5 as 2 in the power of minus 1, right? So 0.5, let me rewrite this, minus ln of 1 over 2 over x, or it can be written as a 1 over 2 as 2 in the power of minus 1, right? And this minus 1 can go, the power minus 1 can go down to here. So it's going to be, so ln of 2 over x. So I've got this formula. So this is equal to the mu. So the another formula would be, so do you see, so I need to take a ln from this part and from this part in order to find the mu, right? So it would be perfect for me if the I over I0 would be the power of the e, right? For example, e in the power of minus 1. So if I over I0 is equal to the e in the power of minus 1, which is roughly is equal to the 0.37, then ln of e in the power of minus 1 is equal to the minus mu x. So this minus 1 can go down to here. It's going to be minus ln of e is equal to the minus mu x. So this minus and minus are going to be cancelled. Ln of e is equal to the 1. Then I can find that the 1 is equal to the mu x, or simply mu is equal to the 1 over x, right? So if I know the x when the current intensity is the 37% of the initial one, then I can find the attenuation coefficient by just taking its reciprocal. For example, here, so this is roughly 0.37. So the current intensity is the 0.37 multiplied to the initial one, right? Or 37% from the initial one. Then I go to here, head the curve, and find the x. It's going to be 2 roughly, right? Or exactly 2. Then the mu, the attenuation coefficient, is going to be 1 over 2, or 0.5, which is going to be roughly equal to this value. So now it appears we can find the value, the attenuation coefficient, in two different ways. Either I find the x when the intensity is the half of the, so the current intensity is the half of the initial one, or I find the x when the intensity, the current intensity, is the 37% of the initial one. So let's do a couple of problems in order to understand how it works. So let's assume that 6 multiplied to the 10 in the power of 7 gamma ray photons under this 2 centimeter thick layer. What will be the number of the gamma photons passing through this layer if the attenuation coefficient is 1.42? So basically, some number of the gamma ray photons are entering the 2 centimeter thick material. I would like to know what's going to be the intensity high here after it passes through this material. So if I know the initial one, okay. So I just need to use this formula. So I is equal to I0 e in the power of minus mu x. So we are given all the parameters here. So I0 is 6 multiplied to the 10 in the power of 7 multiplied to the e in the power of minus 1.42 multiplied to the x is equal to the 2 centimeters, right? So here it's 1.42 1 over centimeter multiplied to the 2 centimeter. So let me calculate this using a calculator. It's going to be exponential of minus 1.42 multiplied to the 2 multiplied to the 6 e in the power of so 10 in the power of 7. It's going to be 3.5 10 in the power of 6. Okay, so this is what we are going to have after 2 centimeters. So let's try to solve a more difficult problem. So the attenuation coefficient mu is given as 0.54 1 over centimeters. The intensity of 370 units was measured after the beam passed a 4 centimeter thickness layer. So first of all, we need to find the initial intensity, and then second of all, we need to find the thickness for which I is equal to the 750 units. So let's find the first one. Again, we always are going to use the same formula. I is equal to the I0 e in the power of minus mu x. So here, at this problem, initially we are given this mu, we are given that intensity is equal to the 370 after it passes through 4 centimeters. The only thing which we don't know is this I. We just need to find this I. In order to find this I, so this E should go to here, right? So I just need to basically divide both of the sides to the e in the power of minus mu x. Okay, so it's going to be I over e in the power of minus mu x is equal to the I0. So since the e is in the power of minus mu x, so it can just go up. So I can write this as the I0, it's going to be I multiplied as the e in the power of plus mu x. So since it's going up, or to the numerator. So then I just put everything to here. It's going to be I is 370 multiplied to the e in the power of mu is 0.54 multiplied to the 4 centimeters. Let me calculate this. It's going to be 3,000 208. Okay, so it's the initial intensity. So in the second part of this problem, we need to find the x. What's the x? At which thickness level x? So the current intensity is going to be 750 units, right? Again, we're going to use the same formula. So the I is equal to, let me write this with a different color. I is equal to the I0 e in the power of minus mu x. So now we know what's a mu. We know the initial one. We just find this here. We know the I, it's given here. So the only thing which we don't know is this x. So in order to find this, we just need to get rid of this e. Okay, so let me find this. I over I0 is equal to, so basically I0 goes to here, goes to the left hand side, e in the power of minus mu x. We take a ln from both of the parts. It's going to be a ln of I over I0 is equal to a ln of e in the power of minus mu x. Come on. Then this mu x is going to here. It's going to be a ln of I over I0 is equal to minus mu x ln of e. So ln of e is equal to the 1. Then from here we can find the x. So x is going to be minus ln of I over I0 multiplied to the 1 over mu. Let us put everything to here. So it's going to be minus ln of I is 750 divided to the initial one is 3208 multiplied to the 1 over 0.54. So let me just calculate this using a calculator. It's going to be ln of 750 divided to the 3208 divided to the 0.54. It's going to be 2.69 centimeters. Well, so at the thickness level 2.69 centimeters, the intensity is equal to 750 units. So well, in this lecture we considered what's the exponential decay, what's the attenuation coefficient, what's the intensity of the radioactive beam, and solve a couple of problems on this.